you start as a junior in freelance, how do you learn? You don't have someone senior to teach you.
There's two ways that you can really learn fast. One is to have a great mentor or a great mentor team. Another option is to do things that are way too hard for you. When you predict energy production in renewables, especially in wind, higher energy is harder to predict. If you have high wind, it also means that there's more gusts, and if there's more gusts, there's more variability. So it's much harder to predict the actual energy production.
When you don't have labels, for example, in credit scoring, where you're lending money for 2 years and you don't know how your model is performing, and you don't know if it's decreasing or not, how can you use monitoring and NannyML to tackle those issues? This is probably the most complete LLM course I've seen so far, from beginner to advanced developer by Towards AI. It's basically a one-stop conversion for anyone who wants to become an LLM developer, and the course has over 90 lessons to go from beginner to advanced in the field. It's both very practical and industry focused, but also quite technical, and you will cover a lot of technical topics like RAG, fine-tuning, agents, audio, and caching. So if you're interested, check out the link in the description, and don't forget to use the code AIStories10 to get a 10% discount. All right, so hello everyone, and welcome to the AI Stories podcast. I'm Leiser, I'm a senior data scientist at Artifact, and I will be your host. So today our guest is Wojtek Kuberski. Wojtek did a master and a PhD in AI at KU Leuven in Belgium, and after that he launched his own freelance brand, Prophecy Labs. But in 2020, he quit freelance and decided to found his own company, NannyML, where he is now the CTO. For those who don't know NannyML, it's a platform for post-deployment data science, also known as model monitoring. And so this conversation will be all about post-deployment data science and monitoring. If you enjoyed this episode, please subscribe to the AI Stories YouTube channel, comment, share, and leave a 5-star review. All right, so let's start now. Hi, Wojtek. Very happy to have you on the show. First thing I wanted to ask is, how did you get into this world of data and AI? How did you get into the field?
Hey Neil, thanks for the intro. Just a small clarification. I actually did not finish my PhD, so I don't have the credentials. I did start it, but I decided to drop out freelance. As for how I got started, so I did my bachelor's in mechanical engineering, and at some point I realized that I actually like the mathematical optimization part of it more and the maths more than the machines. So then I decided that I want to go into either optimization or machine learning. I applied to a million different universities, and I got lucky enough that I got accepted to KU Leuven. Interestingly, I got accepted to Masters in AI, but I got rejected from Masters in Computer Science, which is normally a prerequisite for the Masters in AI, which doesn't make too much sense, but that's how they did it. And yeah, that's kind of how I got started. I studied a bit Python before to not be a complete greenhorn when I started studying AI. Yeah, that's pretty much it.
And so then, you mentioned you started a PhD, but then decided to quit. Why did you decide to quit?
So there were a few things. Part of it was personal reasons. I was really not getting along with my supervisor or promoter, I think it's called.
Okay.
That was one thing. And I think the topic was not honestly very, very interesting. It started as something that was like half of it was interesting, half of it wasn't. But then my promoter was really pushing me into the part that was not interesting me much, very like geometrical stuff. And I wanted to do machine learning. So I started looking for jobs. I got lucky enough that I got few job offers at the same time. And decided to kind of accept them all and start freelance / consultancy, which worked quite well. I don't think you could do it nowadays in the current market conditions, but back then data science was very hot, and you could get away with a lot of stuff.
I mean, why not do it today? Like, there are still lots of freelance now.
Of course, but I think if it's your first job, so I did basically as a first job, right? I think right now there's just so much more supply in the market, so many more data scientists. And of course, the number of jobs in data science is increasing, but I think that the pace of like increasing jobs is not keeping up with the pace of new data scientists that want to enter the market. So it's not as easy to, for example, just take 3 jobs and do them because you're competing with many more people than let's say 8 years ago or a while ago. It's just a more mature market, and I think calling it the sexiest job of 21st century uh, maybe attracted a bit too many people for what the market can handle.
And so you accepted 3 jobs at once. Like, did you do that? Did you start alone, or did you hire people to help you with those projects? How did this beginning of freelance?
Yes. So I was very explicit that like I'll be working in other places as well. And luckily, the people that were giving contracts were quite accepting of that. I think first few weeks I was alone, but then I started hiring. Also, Hakim, my co-founder at Profis Labs, and then also at NannyML joined me very, very early on. So that helped a lot. So we kind of shared the work. He also started getting his own contract. We started hiring people. And I think after a year, we were 11 or 12 people. So that was quite a nice growth. But then after COVID came, we had to downsize a bit. And that was a good opportunity to jump into a product company, into NannyML.
But still on the freelance, I'm keen to dive maybe a bit deeper into like 1 or 2 projects that you worked on. What were the kind of project that you did at the time? What did you work on?
So it was really kind of across domains, across industries, across everything. There was one of the, I think the more successful projects that I did was for a company called Darts IP, where we were developing classification systems for documents.
Okay.
That was very, very interesting. There was also a part for a Swiss company in ad space, where we were working on basically figuring out who saw a given ad. So there was a lot of geospatial data, and in the other company, the legal company, was mostly language data. I didn't do it much myself, but I was mostly supervising a project and kind of helping from lead perspective in computer vision in automotive industry, where we were doing basically background removal that had to be pixel perfect, which was not an easy task in 2017 or 2018. Right now, you just put it in, remove background or one of the pre-trained networks. But back then, we had to train stuff from scratch, figuring out how all these pyramid networks work. That was quite cool as well.
How did you do that at the time? Like, obviously now you've got Gen AI models that can do this, but was it still CNNs at the time, convolutional neural networks?
Yes, so these were convolutional neural networks, and there was, I think it was called a pyramid structure. Basically, what you do is you first encode it into a low resolution, then you run it through a CNN, and then you like super resolve it back. And basically you do pixel-wise classification whether something is a background or not background. That's how like all the background removal networks actually work under the hood. If you look at whatever Zoom and you remove your background, the network that is there under the hood also does the exact same thing. We just had to train it from scratch, and luckily we got a few years of data because the customer used to do it manually with a team of few people, where basically graphic designers would manually remove all the pixels that needed to be removed. So we had the original photo and basically de facto the label was background, was the background pixel level. So we could train the model on a few million examples there. And that ended up working quite nicely. One of maybe an interesting piece of trivia there is that we ended up deploying on a gaming laptop because that was the easiest way to get around IT requirements. We just gave the customer a gaming laptop with a strong GPU that could handle the network. Yeah.
Okay, so cool. You had some fun projects, it looks like. How, and one question that I ask myself is, yeah, if you start as a junior in freelance, like how do you learn? You don't have someone senior or a manager to teach you, technically speaking, how to do things or to improve your code quality or whatever. So how did you learn and progress? And
Yeah.
was this not an issue?
So that's a very good question, and I think like in general, there's two ways that you can really learn fast. One is to, like you said, have a great mentor or a great mentor team, work in a company that is at the tip of the spear and really sets the standards. Another option is to do things that are way too hard for you, and then you basically have no other option but to learn. And I think when I was getting started a few years ago, that was what most data scientists had to do, because most of the time you were the only data scientist at the company, right? Or maybe if you got lucky, you were working one or two more, but data science departments were not a thing back then. So basically the point was that you get started, you have a project, and you need to figure out very fast what is the actual business goal, how to solve it. So there was a lot of blog reading, paper reading, and then also talking with the business, which also means that for me, there's always something that has to go, right? You cannot do it all. So I never learned how to be a proper coder. I never did production ready code. I was able to figure out what is the actual business need and how to frame it correctly and how to translate it into business requirements, which is something that you just learn by, I guess, talking with business stakeholders. And then you read a lot of papers and blogs and try to code things in a very easy way.
But you took on projects without really knowing how to solve them when you took them out?
Absolutely. I think that was the case for all the projects. The first project in computer vision, I've never done anything in computer vision apart from one neural networks class at the university when we learned that CNNs exist, but we actually never coded the CNN, I think, back then. Same with natural language processing. The legal documents project was also, I never had any experience there. I mean, you just look at PyTorch. How do you get started with it? You start coding. I think the most important thing is to kind of focus on two things: the maths behind it, to really understand how these networks work, and not just do from PyTorch import X. And another thing is to actually try to do it yourself on real data from scratch. And if you have these two things, you will understand why it works, why it doesn't work, and you'll be able to actually see the results in practice. And these are kind of the key things. What I would always advise against is to try to just go through the steps of something that somebody has already done on a known data set. Don't build another, Titanic prediction. Find yourself a data set. Do something that will require you to actually think and struggle. If you just click on the things that already exist and you already know what the next step should be and you just copy paste the next step, you will actually not learn how to solve problems that you'll have to solve in a real job.
And so you do a bit of freelance, a couple of years of freelance, and then you decide to quit and launch NannyML. So can you go through this process? Why did you stop freelance and why did you launch NannyML? How did this idea of model monitoring came up?
Yeah, so that was actually kind of a perfect storm. The stars really aligned. First, we were always, like me and Hakim and then another co-founder joined later, William, we were always trying to find ideas, potential product ideas based on basically what customers wanted. And what we kept on hearing over and over again is that people wanted to make sure that these models will keep on working after, we build them for them, we build the models for them, and then we deploy it for them. And then we finish the project, right? That's how consulting works. And then we move on to the next project. But they really wanted to make sure that these models keep on working. And it's not something that we felt in any way comfortable doing via services. we knew that we needed kind of a framework, a way of monitoring them at scale. So that was kind of a natural product idea, and we already knew that there is need in the market. On top of that, we got lucky enough that a CTO at the time of Colibra, one of the few Belgian unicorns and one of the very few Belgian unicorns in data, was our mentor. And he's been always pushing us to already drop consulting and go into product. And then at the same time, we lost two biggest customers due to Corona, because they were like tightly coupled to going outside. They were businesses that really focus on you need to be outside to do stuff. One of them was working in ads, outdoor ads. You don't really look at outdoor ads. Another one was a housekeeping service, and you don't necessarily want a housekeeper in the middle of the pandemic. So
makes sense.
We unfortunately lost them, and that kind of gave us the access to venture capital that we needed to start a product company through our mentor, a validated business need that we already had from our existing customers, and kind of the economic reason to step out of the golden cage of consulting and do something else because we suddenly lost the biggest customers.
So some quite good reasons, I guess, to start a business. And I mean, I know a bit NannyML, but for those who don't know, what is it doing, and maybe even before that, actually, why do you need model monitoring? Like, how do model fail, and why do you need monitoring?
Perfect. So in a nutshell, what we generally say to less technical people is the world changes, and that means that the data your models is consuming is also going to change, and the models that you train are not necessarily or generally are not trained to handle any kind of data, any distribution of the data. So that means that your models will no longer be able to predict well. If you train them to only find pictures of cats in the snow, but you see a picture of cat in the desert, it is quite likely that it won't perform as well as it used to. And this is something that's very easy to spot if you look at pictures of cats. But if you do credit scoring for a huge bank, or if you do, let's say, demand prediction for a supermarket, then of course this is something that can kind of sneak past you, and you will see that your model used to perform very well and performs still very well on your test set, but on real data, the model performance drops significantly, and you might even be better off not using the model at all than using it in the current state. So this is
that's the case. Sorry, that's the case when the distribution that you see during testing is different. The data distribution that you see during testing is different than the data distribution that you use to train your model, right?
So not only testing, but you're correct. This is a distribution shift, also known as covariate shift. So the distribution of your features changes. But the most important part is really not the testing, but the production data. Your training set and your testing set might have roughly the same distribution. You see that it works well. When you deploy it, it still works well. But a few months later, the distribution of the real world data that your model ingests and makes predictions on might be completely different.
Okay, makes sense.
And go ahead.
No. So I was gonna ask, are there other methods of failures? I guess there are.
Yes, perfect. Indeed. I was just going there. So that is covariate shift. And then the kind of second main way how your models can fail is so-called concept drift. When the relationship between your model inputs and your targets, the thing that you're trying to predict, so let's say maybe whether somebody is going to default on their loan, has changed. And that is something that's even harder to detect, especially detect fast enough, because in general, in production, you do not have access to the labels, right? And this is something that a lot of especially junior data scientists just don't take into account. But not only juniors, also a lot of senior people don't really think about it. And the kind of key problem here is that during testing, you always can evaluate the quality of your predictions. But when you deploy your model to production and you say you want to predict whether a person is going to default on a mortgage in, let's say, 2 years, then you actually have to wait 2 years until you get any kind of label, any kind of target data. So you cannot just simply measure the performance of your model because there's no labels to compare the predictions to, which is, I would say, at the heart of model monitoring and kind of at the heart of post-deployment data science. How do we still get a reasonable indication of the model performance without access to these targets, without access to the ground truth? And the way we do it is that we can actually quantify the impact of this feature distribution or covariate shift on model performance. And at NannyML, we came up with a couple of algorithms that can do that. Happy to talk about them later. And then when it comes to concept drift, so this change in relationship between model inputs and the targets, for that, we really need to wait until we get the feedback, the target data. But luckily, in practice, it happens less often than covariate shift. So detecting the impact of covariate shift tends to be sufficient, let's say, in most cases, some cases.
Because personally, what I usually do, or what I did in the past, is monitoring the inputs to your model. So understanding a bit, does the distribution of a feature vary over time? Because you know what was the distribution of all features during training, and so you can check if during testing or in production, those distribution change or not. So you can monitor the input. The second thing is also monitor the output, see if the distribution of the output varies or not. And then, look at a couple of metric. I don't know what's the maximum, what's the minimum. You can sometimes you also have the target. In some cases, you've got access to the target, or in some cases, you need to wait, but then you have access to the target. So also, when you can obviously monitor the performance of your model, like whatever metric you're using, how is this metric performing? Is the metric in production the same as what I got during training? And also try to ask a few users, how is the model? Do the decision make sense? So that's what I try to do. But you're saying there are additional things that should be done, or this doesn't solve everything?
Absolutely. So I think talking with the users is always kind of the best thing you can do. It's hard to scale, of course, and it tends to be quite expensive in terms of man hours, because then you're spending your time, and that always costs money. But it's definitely something you can do if you have access to lagged metrics. If you can calculate your accuracy of one or whatever, you should absolutely do it. And this is one of the best things to monitor. However, as I said, in most cases, the ground truth or the target data is delayed, so you won't be able to monitor that. And then indeed, it's quite natural to start looking at the distribution of the inputs.
Mm-hmm.
But there is one really big issue of it, which is the models are generally quite robust to change in the input distribution. And if you just look at and investigate every change in any of the features, let's say your model has 50 features, or in financial data, 200 features, you will just be drowned in false alerts. There'll be things changing all the time. Maybe they will even be statistically significant, but just because something is statistically significant doesn't mean that it actually impacts model performance. And we wrote a few blogs about it. We did a bit of research there. And indeed, what we see is that vast majority of covariate shift, so change in the distribution of your features, does not actually impact performance. And the relationship between, let's say, drop in your F1 score has very little to do with severity of the drift. If your data moves to a region where the model is really not performant, but this region is very close to your original data distribution, you will not see a lot of drift, but you will see a huge drop in performance. And kind of conversely, imagine that you have a classification setting and your data moves away from the class boundary. Then you will see a very strong potential, very strong covariate shift, very strong, let's say, any metrics that you use, let's say KS test, they will all spike, but the model performance will actually improve a bit. So it's not a problem at all. Everything is fine, but you are either missing important alerts or focusing on stuff that doesn't matter. So it's really important to quantify this impact of covariate shift on model performance. And I can go more technical later on if you're interested.
Yeah, I mean, I'm keen, still high level, but I'm keen to. So basically, when you don't have labels, for example, in credit scoring, where you mentioned you need to predict if someone is going to repay in 2 years, and so you need to wait 2 years, and so you're lending money for 2 years, and you don't know how your model is performing, and you don't know if the performance is decreasing or not. How can you use monitoring and NannyML to tackle those issues, and how can you know if the model is performing well or will perform well if you don't have the label? It seems a bit magical to be able to understand that.
Absolutely. It also seemed impossible and magical to me for a while until we finally figured it out. And yeah, the key, as already mentioned, is that we can actually see what is the expected impact of data drift on model performance. And ideally, I'd have a whiteboard to show something, but I'm going to try to describe it in visual language, let's say. Imagine that you have a classification model for defaults. What you would expect to see if you have any experience with classification models is that if your data is very close to the class boundary, then it's going to be very hard to make the correct prediction, right? Because there's no information in the input data about the target. And if your data moves away from the class boundary, then it's going to be easier and easier to make the correct prediction. Classes become basically separable. And now what we can do, instead of just measuring the magnitude of the drift, if we measure where the data actually is and what is the expected level of performance in that particular point in your model input space, then you can kind of actually compute the expected metrics. So you can compute your expected F1, you can compute your expected ROKUC, you can compute for regression models, maybe mean squared error. And you can do it for every point in the model input space. If you just know what is the predicted probability, what is kind of the performance on your test set in that point in space, you can kind of quantify that intuition, and then you can say that we expect that if the data points are within, let's say 0.1 of the class boundary, we expect the model F1 to be 0.3. If we get more data points there, then we just kind of weigh how many points are very close to the class boundary, how many points are further away, and we can get a reasonably good expectation of what the model performance is. There is a lot of details there related to probabilities and calibration and making sure that these probabilities are actually correct. But on the high level, I think that's a reasonably good intuition.
Okay, and so you, then I get back to the main question, like, what do you do in NannyML? You've got this algorithm that can estimate the performance of your models, even if you don't have labels. Do you have other algorithms? Do you have a platform? What do you do, and how do you leverage those monitoring algorithms?
Absolutely. So this is kind of the key. You always need to start with your performance. When you have access to it, you get access to it. If you don't, you can estimate it. And we have a couple of algorithms that we developed, and we actually just got a paper published in JAR, Journal Artificial Intelligence Research, recently with University of Helsinki about one of them for classification. So if you want to go really deep, you can check it out. And that's kind of the starting point. Then you know whether there is a problem, right? So you get the visibility into your issues. But that's just the first step. Then you actually need to resolve those issues. And then what we have is we have a cloud version of NannyML that allows you to basically interact with the dashboard and kind of guides you through this root cause analysis process. And first, you see what are the potential reasons why your model performance has dropped. First of all, actually, whether your performance has dropped. Then the reasons. And the reasons there, we have basically a suite of drift detection tools. So we can detect concept drift, changing the relationship again, or we can detect, just like you were trying to do when you mentioned how you do model monitoring, which features are drifting. And that kind of is very useful, not as a way to see whether there is a problem, but to actually troubleshoot what the problem is. Then you basically have few metrics that can give you the measure of drift, how strongly a different feature behaves, different feature looks like, different feature is distributed. Also, some basic data quality tools, and now we're going a bit deeper in terms of product development into those data quality tools, because quite often the actual root cause is that your data quality has dropped. It's not the actual distribution, but just the quality of your data. And then we kind of take it all together and lead you through the process that allows you or helps you find the actual root cause, which might be data quality, might be specific covariate shift in some of the features that then you can use to either retrain the model or just adjust how your model is affecting reality. Maybe you put slightly tighter constraints, maybe you put a human in the loop to make sure that the model still performs well. And kind of that forms this core machine learning monitoring flow, where you start with performance, either monitoring or estimation. Then you go to the root cause analysis and you look at concept drift, covariate shift, and data quality. And you find which of these issues is the most pronounced, most correlated, and potentially most causal of the drop in performance. And then the last step is kind of resolve the issue, either via retraining, either adjusting the downstream effect of the model, how model operates in the real world, or resolving the data quality issues upstream. And that's kind of what NannyML does as a product. There's also an open source library when all these parts or most of these algorithms are there, not all of them, not the newest ones that we keep in the cloud for a while. But then you need to kind of piece the puzzles together and figure out what's going on, but you have all the signals there as well.
Okay, cool. So a monitoring platform basically where with dashboards, I guess, where you can see the performance of your model. The most important is detecting whether your model is performing well or not. But on top of this, if your model isn't performing well, you've got processes to understand the root cause of that, whether Absolutely. It's a data quality issue or shift in your features or whatever.
Absolutely.
How do you find this? Like, how do you know? Okay, we know we see in the dashboard there is a shift in performance. Two questions here. One, what do you mean by data quality issue? How do you analyze that? And two, how do you find this root cause? How do you know where it's coming?
Mm-hmm. So maybe starting with the easier one, which is the data quality. We have a couple of like super simple metrics, the ratio of missing values in your data set. If it used to be 2%, but now it's 20 for that feature, probably something's wrong with your data pipelines, right? Or if you used to get 20,000 new data points a day and now you get 200, it's probably not that your demand is drying up, but there's something wrong with your pipelines, right? So these signals are generally quite easy to detect and kind of pin down that this is indeed data quality. Then we have these kind of ambiguous signals, like the distribution of your data has shifted. Is it because there is more zeros now, or just the world is different, right? And the data is still correct. For that, we have visualizations and plots. So you can basically look as a data scientist how the distribution actually looks like and how it used to look like before and whether that change is most likely due to data quality or not. Now, when it comes to kind of tying the model performance drop to specific signals, that is the hardest part and it's something that we're still actively working on. So it's definitely not a solved problem. The simplest things you can do is just correlate over time a specific data quality or covariate shift or concept drift measure with model performance. And then if you can see that this particular feature that is important, and whenever it drifts, model performance changes, maybe not necessarily drops, but changes, then you can potentially say that, of course, there's association, but you can maybe be a bit bold and say that there's even a causation there. Of course, there's no proof for that, but then if you, let's say, look at this feature, see there's some data quality issues with it, you resolve those and model performance increases, you solve your problem. But a lot of that is still a mix of, science and art. like most data science is. So we basically give you tools to see how things look like and how they evolve in time, and simple measures of correlation, etc. But then it's also very important to actually understand what these columns mean. So we still need human in the loop. That is kind of the main job of a data scientist that works post deployment, to really figure out what's going on. And then kind of at the end of the scale, on one hand, the hardest thing, but also the easiest to interpret, is the concept drift, where we can actually, that's yet another algorithm that at some point we should write a paper about, that we can actually quantify the impact of concept drift on model performance. How we do it is a bit more complex, so I'm not going to go into the details here, but there you can actually see in basically, I'm going to risk it and say causal way, see the impact of concept drift on any of your metrics. So you could see that your F1 dropped 30 percentage points because of concept drift. And then if it's concept drift, it's also one of the kind of most actionable and direct signals, because this is the only time when retraining will help. If you retrain your model on a new concept, it will learn the new concept and the model will improve. If you retrain a model on bad quality data, the model will probably get even worse. So retraining is not a silver bullet. If you retrain your model on different distribution, but the distribution is just in a place where there's less information about the target, right? Let's say very close to the class boundary, you will not improve your model performance because there's no new information in the data. So that's why the concept drift detection is so powerful, because it can directly trigger a retraining loop, and then it just works. And your model gets better.
Yeah, I think that's a super important point, because it's many data scientists believe that retraining solves all problems, and if you just retrain your model constantly and frequently, then everything will be fine. But yeah, there are still things that the model cannot solve, and sometimes if you don't monitor your data quality, for example, you can retrain your model as many times as you want, it's still not going to perform well. So yeah, retraining doesn't solve everything.
Exactly. We even had an early design partner a few years ago, where we basically run machine learning monitoring for them to really learn what are the issues and what are the problems. And what we noticed is that they had a data quality issue that they were aware of a few months ago, but what they were not aware of is that they retrained the model on the bad quality data. Then the data quality was improved, but the model was not retrained. The bad quality data was still used to retrain the model regularly. And then model performance dropped significantly. I think it was, let's say, ROC-UC dropped by around 5 percentage points for a few months. And they were actually not aware of that because the labels were always delayed and they didn't have good monitoring in place. But then retraining actually made the issue worse, right? Because the data quality was resolved, but because the model was worse, it predicted worse even on good quality data. So sometimes retraining is worse than not doing anything.
Yeah, and I, like on the side note, in a company that I worked on, we had at the beginning no monitoring in place, and so when I worked on a project and realized on a model, improving a model, and realized that like one key feature was completely missing from this model, like it wasn't fed into the model. And so that's why if you don't, I mean, monitoring is just the first thing you should do when you deploy a model, because very bad things can happen. And yeah, your model will make predictions, but if they're not useful or if they're wrong, well, it's things very bad can happen to the business.
It's the worst kind of failure. It fails silently. It still makes predictions. You can still act on it. It still looks like it's fine. From like pure engineering perspective, it does work fine, but from business and data science perspective, you get failures and you really won't notice them unless you monitor your models.
So actually, how do businesses use your platform? Like, how do they connect their models or their predictions to your platform? How do they use it?
Yes, that's a very good question, and it's very important for a lot of bigger enterprises. And basically, what is really important for a lot of bigger businesses is that data does not leave their clouds. So what we do is instead we deploy NannyML cloud inside their environment, where they can completely firewall it. And ideally, of course, we'd like to collect metadata, how they use the product, but it's something that they can completely turn off. And actual user data or whatever data they use to make predictions never actually leaves their cloud. And NannyML operates completely within their system, whether it's Azure, AWS, or Google. And basically what you do is you just point to where the model inputs are, where the model predictions are, and where labels are if available. And NannyML will ingest them on a schedule that you specify. And then it will alert you on drop in any key performance metrics that you specify. So then you can connect that with Slack, PagerDuty, whatever you want. You can send emails, etc. when there is an issue. And then if there is an issue, go back to the dashboard and you see exactly what happened, how the kind of historical evolution of the metric looks like. And then you can delve deeper and see what are the potential root causes in covariate, shift, concept-driven data quality.
Okay, cool. But you don't need, because the cool thing is you don't need to deploy your models on your platform or whatever. You leave your models where they are, and then your platform is just plugged in where it takes the inputs, outputs, labels, and deals with it.
Yes, and that's actually maybe one more thing that's worth mentioning. It is that we don't actually consume the models themselves. We only look at the model inputs and outputs, which means that NannyML is completely model agnostic. You can deploy a scikit-learn model, stats model, PyTorch, huge pre-trained network written in Scala, who knows? And we really don't care. We just get model inputs, model outputs. And the only thing we need to have is access to the data. But again, the data still always stays in customer cloud.
So what are the next steps for NannyML? Have you solved model monitoring? What are the big challenges that you're thinking about?
Yeah, so what we have on the roadmap, there's a couple of things. Like I already mentioned, one really big thing is this kind of causal relation or root cause analysis of the issues. Right now we have a couple of solutions there, but they definitely require further development. Another thing is right now we're mostly focused on tabular data. NannyML can work on image data and language data, but there is still limited support for it. So we're focusing on expanding to have like full support, especially when it comes to interpretability, to really figure out, give a specific examples of pictures that the model is not performing well on, what are the typical characteristics of those images, etc. So kind of root cause analysis, because performance estimation works out of the box on any type of data. But for the root cause analysis, we're developing a bit more tools for that.
Okay.
And then last thing is what we noticed is that there is a lot of kind of time patterns in model performance, which can potentially, again, trigger false alerts. Maybe, that's another actual real example, is that when you predict energy production in renewables, especially in wind, higher energy is harder to predict. If you have high wind, it also means that there's more gusts. And if there's more gusts, there's more variability, there's more, chaos, fluid dynamics, etc. So it's much harder to predict the actual energy production. And it's kind of, seasonal. You have more winds in specific times of the year, depending where you are geographically. And that means, for example, that maybe your model performance will drop always every summer. And there's nothing to worry about. So we're also looking at this kind of time series analysis of performance to reduce those false positives and false negatives and really give you the real signal and exclude seasonality, exclude the noise. But I think the main thing is really focus on other data types and the root cause analysis. And of course, data quality.
And Gen AI, so do you plan to look into Gen AI at some point as well? I know that monitoring is a big challenge.
There is one thing that was absent there in the Gen AI. So we did quite significant research on it, and I already gave a few talks on Gen AI monitoring. And what we see right now is we focus on this kind of classification-driven and then natural language processing. even if there is a Gen AI model, that that is underneath it. But what you get most of the time in big enterprises, the use cases are still not necessarily about generation. For the use cases that are about generation, we have it kind of on the roadmap, but we're still honestly waiting for getting kind of market confirmation that Gen AI models are past the POC stage. Because of course you can throw a lot of budget and put all the teams working on the POCs, but Gen AI needs to actually be deployed in production to bring value and to need monitoring. And we see that there is progress there. It's happening, but it's happening much slower than I think everyone had expected. I don't know, Neil, maybe, if there's any already Gen AI use case at your company that are already in production and actually delivering value.
Yeah, there are some. There are definitely some in production, but I agree with you that many are still in the POC phase, and going from POC to production is a challenge, a much bigger challenge than when you build a forecasting or a scoring algorithms. I see some in productions that are delivering value, but it's I agree with you that lots of projects are still in the POC phase. Going to production is a challenge, and there are still lots of challenges like robust monitoring and even evaluating the model. Maybe that's the biggest challenge. Like
Yes.
in forecasting, you've got those metrics, or in scoring, if your model, if you have the label, if your model is good or not. In Gen AI, it's super difficult. Like, how do you evaluate a conversation with a client? So the evaluation is difficult.
That is actually the place where I think we made already the most progress, and the closest thing on our roadmap is going to be evaluation in production.
Cool.
So not like necessarily, monitoring every single output, but just knowing whether your model is actually working fine. That's going to be the first thing we do. It's still going to be after the support for the image data in general. Root cause analysis for the text data, but it's going to come right after that, most likely.
Great. So looking forward to the coming changes then. We'll leave a few links to NannyML, to your website, and to some of the blog posts in the description. Maybe one last question before we finish the episodes. More career advice, but if you had one advice for people to progress in their career, just one advice, what would it be?
Do what you're good at. Focus on strengths, not weaknesses. I think there is way too much talk about showing up your weaknesses. And what you see that people that are very successful, they focus on what they do well and let other people fill in the blanks and fill in the gaps. And I think that's the main thing. If you're really good at maths, focus on maths. If you're really good at programming, focus on programming. If you know how to talk to business and understand that, focus on this. You don't have to do everything.
Well, Wojtek, thanks a lot. It was great to have you on the show. Have a great afternoon, and hope to catch up very soon.
Thanks a lot. It was great to be here.
Thank you.